The Pacific Ocean stretches before us like a vast liquid mirror reflecting the fading light of day. Waves roll across its surface in endless procession, each one a whisper of wind made visible, each one carrying the memory of storms born 1,000 miles away. But beneath this tranquil surface lies a truth written in fire and stone, a truth that rises 13,000 feet above the waves and plunges 19,000 feet below them. This is Mauna Loa, the Long Mountain, the largest active volcano on Earth. For millennia, it has shaped the Hawaiian Islands with rivers of molten rock, building paradise one layer at a time. Its slopes are gentle, deceptive in their gradual ascent. From sea level to summit, the climb is long but never steep, a warrior's shield laid upon the earth, as ancient Hawaiians observed. But Mauna Loa is not merely a mountain. It is a monument to the planet's restless power, a reminder that the ground beneath our feet is never truly still. It is a geological giant that has been erupting for at least 700,000 years, building itself higher with each convulsion, spreading itself wider with each breath of fire. This is the story of Earth's greatest shield volcano, a giant that has erupted 33 times since 1843, threatening communities, reshaping landscapes, and revealing the raw mechanics of our living planet. It is a story of fire and stone, of danger and beauty, of human resilience in the face of elemental power. The mountain is patient. The mountain is persistent. And the mountain is far from finished. The Hawaiian archipelago emerges from the Pacific like a string of emeralds cast across blue velvet. 8 major islands, each one a testament to volcanic birth, stretch across 1,500 miles of open ocean. From the northwest to the southeast, they march in order of age. Kauai, the Garden Island, worn smooth by millions of years of erosion. Oahu, home to Honolulu and the extinct craters of the Koala Range. Maui, with its massive Haleakala volcano, dormant but not dead. And finally, the Big Island, Hawaii, itself, the youngest and largest of the chain. But these islands are not random. They are breadcrumbs, marking the slow journey of the Pacific Plate over a deep geological furnace. They are the visible scars of a process that has been occurring for tens of millions of years, a conveyor belt of creation that stretches back into the planet's ancient past. The native Hawaiians knew this landscape intimately. They called the volcano goddess Pele, and they understood that the land was not permanent, it was renewable, constantly being created and destroyed in cycles as old as memory. Their chants and legends speak of Pele's journey from island to island, seeking a home where she could build her fires without her sister, the sea goddess Namaka, drowning them with waves. According to tradition, Pele finally found her permanent home in the Halema-Uma-U crater of Kilauea, the most active volcano on Earth. But her influence extends across all the volcanoes of the Big Island Kilauea, Mauna Loa, Mauna Kea, Wabula, and Kohala. Long before Western explorers set foot on these shores, the Hawaiians witnessed Mauna Loa's power. They watched orange rivers carve new paths to the sea. They felt the ground tremble beneath their villages. They saw fountains of fire shooting into the night sky, painting the clouds in shades of crimson and gold. They adapted their lives to the rhythm of the volcano, building their society around the certainty of change. Villages were constructed with the understanding that they might need to be abandoned. Gardens were planted knowing that they might be buried under rock. Fishing grounds shifted as new lava extended the coastline into the sea. The Hawaiians developed a sophisticated vocabulary for volcanic phenomena. Pahoehoe smooth, ropey lava that flows like thick honey. Ea, rough, jagged lava that clinks and clatters as it advances. Pele's hair-fine strands of volcanic glass drawn out by fountaining lava and blown by the wind. Pele's tears, small drops of lava that cool into smooth, teardrop-shaped glass. This was not merely descriptive language. It was survival knowledge, passed from generation to generation, encoding observations about which types of lava move fastest, which are most dangerous, which can be crossed and which cannot. When Captain James Cook arrived in 1778, he found a civilization that had thrived for centuries in the shadow of active volcanism. The Hawaiians had learned to read the mountain's moods, to recognize when Pele was restless, when the vents glowed red against the night sky when it was time to move. But by the mid-19th century, as Western settlement expanded across the islands, the relationship between humans and volcano began to shift. Towns grew larger. Infrastructure became more permanent. The stakes of each eruption grew higher. Missionaries arrived in the 1820s, bringing Christianity and Western notions of land ownership. Sugar plantations were established in the 1830s, transforming the landscape and economy. By 1843, when reliable record-keeping of volcanic eruptions began, the Big Island was no longer solely Hawaiian, it was becoming a crossroads of cultures, economies, and worldviews. And all of it existed in the shadow of Mauna Loa. Hilo, the largest settlement on the Big Island's eastern shore, sits just 25 miles from Mauna Loa's summit. Founded in the early 1800s, it grew into a thriving port town, its economy built on sugar plantations and shipping. The bay provided a natural harbor, protected from the worst of the Pacific swells. Rainfall was abundant, feeding the plantations and keeping the surrounding landscape emerald green. But Hilo's prosperity came with a price. It was built directly in the path of Mauna Loa's northeastern rift zone. The town had been threatened before. In 1852, an eruption high on the mountain sent flows toward the northeast, though they stopped well short of populated areas. But it was a warning, a reminder of the danger that loomed above the town. In 1855, Mauna Loa erupted again. This time the flow came within a mile of Hilo's outskirts before stopping. Residents watched in terror as the Orange River approached, consuming everything in its path. Trees exploded into flame. The ground shook with the weight of the advancing flow. At night, the glow was so intense that people could read by it, and then, inexplicably, it stopped. The flow simply ran out of momentum, congealing into a black, steaming mass that would take months to fully cool. Hilo breathed a collective sigh of relief. Churches held services of thanksgiving. But the more thoughtful residents understood that they had been lucky, nothing more. In 1881, Mauna Loa erupted yet again. This time, the flow reached the edge of Hilo Bay, close enough that residents could feel the heat radiating from the molten rock. The lava poured into the ocean, creating clouds of steam and acid rain that corroded metal roofs and burned exposed skin. Princess Ruth K. Alikalani, a Hawaiian royal and devoted follower of the old religion, traveled to the flow front and performed traditional chants to Pele, offering silk scarves and brandy as gifts. The next day, the flow stopped. Coincidence? Divine intervention? The simple fact that the eruption was running out of magma? No one could say with certainty. But the story became legend, a reminder that the old ways, the old understanding of this land still held power. Each time the town was spared. Each time people rebuilt a little closer, confident that the next eruption would also miss. This is the peculiar arithmetic of living with volcanoes, the calculation that weighs paradise against peril, that bets on odds that eventually run out. It is the same calculation made by people living on earthquake faults, in floodplains along hurricane-prone coasts. Humans have an extraordinary capacity for optimism, for believing that disaster is something that happens to other people in other places at other times, but geology is patient. And geology always collects its debts. By the early 20th century, the science of volcanology was still in its infancy. Eruptions were documented, but the mechanisms behind them were poorly understood. Why did some volcanoes explode catastrophically, while others, like those in Hawaii, produce relatively gentle lava flows? What triggered eruptions? Could they be predicted? In 1912, Dr. Thomas A. Jagger, a geologist from MIT, established the Hawaiian Volcano Observatory on the rim of Kilauea's summit caldera. Jagger had witnessed the devastation of the 1902 eruption of Mount Pele in Martinique, which killed nearly 30,000 people in minutes. He was determined to understand volcanic processes well enough to save lives. The observatory Jagger built was primitive by modern standards, a single building perched on the edge of an active volcano, equipped with basic seismometers, tiltmeters, and thermometers. But it represented a revolutionary idea, that volcanoes could be studied systematically, that patterns could be discerned, that prediction might be possible. From this vantage point, Jagger and his successors maintained a constant vigil over both Kilauea and Mauna Loa. Every earthquake was recorded on smoked paper drums. Every change in the volcano's behavior was noted in careful handwriting in leather-bound journals. Kilauea, being more active, provided most of the data. It erupted frequently, sometimes continuously, allowing scientists to observe the relationship between seismic activity, ground deformation, and actual lava emission. Patterns began to emerge. Eruptions were preceded by increased earthquake activity. The ground inflated before eruptions and deflated during them like a balloon filling with air and then releasing it. Mauna Loa, by contrast, was more enigmatic. Its eruptions were less frequent, every few years rather than nearly continuously, and they often came with less warning. The mountain's sheer size meant that small changes in any one area might not be detectable with the limited instrumentation available. But by the 1940s, the observatory had accumulated decades of data. Dr. Gordon A. MacDonald, who had worked at the observatory since 1935, was one of the world's leading experts on Hawaiian volcanism. He had witnessed numerous eruptions of Kilauea and several of Mauna Loa. He understood their rhythms, their patterns, their moods, and in early 1950, those patterns began to shift. The first signs were subtle small earthquakes rippling through the Big Island, too faint for most people to notice but recorded with precision by the observatory's seismometers. At first, the earthquakes were deep, originating miles below the summit of Mauna Loa. This was not unusual. The volcano was never completely quiet. But by April, the earthquakes were becoming more frequent. By May, they were becoming more shallow, migrating upward through the mountain's edifice like bubbles rising through thick syrup. Dr. MacDonald and his team recognized the pattern. Magma was on the move, working its way upward through fractures in the rock, seeking a path to the surface. The pressure was building. Tiltmeters instruments that measure tiny changes in the angle of the ground showed that the summit of Mauna Loa was inflating, swelling upward like bread dough rising. This was another classic precursor to eruption. As magma accumulated beneath the summit, it pushed the rock above it upward and outward. But the critical questions remained unanswered. Where would the magma emerge? And when Mauna Loa is deceptive in its vastness, its summit caldera, Moku'io'io, sits at 13,679 feet above sea level, but the volcano's true base lies on the ocean floor, nearly 3 miles below the surface. From seafloor to summit, Mauna Loa rises more than 56,000 feet taller than Mount Everest, making it one of the most massive single mountains on Earth. The volcano's volume exceeds 19,000 cubic miles. Its weight is so enormous that it has actually depressed the ocean floor beneath it, creating a moat several miles deep in the surrounding seafloor. This is isostasy in action, the principle that massive loads cause the Earth's crust to sink, like a person sitting on a soft mattress. This immense structure is laced with rift zones, linear fractures that radiate from the summit like spokes on a wheel. These rifts are the volcano's pressure valves, pathways through which magma can escape when the internal pressure becomes too great. The northeastern rift zone points directly at Hilo. The southwestern rift zone extends toward the Kona coast. The summit itself could erupt, sending lava cascading down multiple flanks simultaneously. Historical patterns suggested that Mauna Loa's eruptions often began at the summit and then migrated to one or both rift zones. The 1942 eruption had followed this pattern, with summit activity lasting a few hours before the eruption shifted to the northeastern rift zone. But patterns are not guarantees. Each eruption has its own character, its own dynamics. The mountain is not a machine, following predictable rules. It is a complex system, sensitive to countless variables, capable of surprising even those who know it best. As June arrived, the waiting became unbearable. Every earthquake was logged in the observatory's records. Every tilt of the ground was measured and graphed. The scientists issued warnings to civil defense authorities, but warnings without certainty are difficult to act upon. You cannot evacuate a city on maybes. You cannot shut down an economy on tremors. The people of Hilo went about their daily lives, glancing occasionally toward the mountain, wondering if today would be the day. Sugarcane ripened in the fields. Ships came and went from the harbor. Children attended school. And beneath their feet, miles underground, magma continued its inexorable ascent. On the evening of June 1, 1950, Mauna Loa made its intentions clear. At 9:04 p.m., the summit of Moku'io'io cracked open like an enormous egg. The seismographs at the observatory went wild, their needles swinging off the scale as the ground convulsed. Within minutes, fountains of incandescent lava shot hundreds of feet into the night sky, visible from both coasts of the Big Island. The glow painted the clouds orange and red, a celestial fire that announced the awakening of the giant. People in Hilo, 25 miles away, stepped outside their homes and stared upward at the unnatural light. People in Kona, on the western coast, saw the same glow reflected off the underside of clouds. Across the island, thousands of eyes turned toward the mountain. The summit eruption was spectacular. Multiple vents opened along the floor of Mokuweoweo caldera, each one producing curtains of fire that merged into a single, continuous wall of lava. The fountains danced and pulsed, driven by the escaping gases dissolved in the magma. Dr. McDonald and a small team made the difficult journey to the summit through the night, driving as far as they could and then hiking the final miles in darkness. What they witnessed when they reached the caldera rim was one of the most powerful volcanic displays any of them had ever seen. The entire caldera floor, nearly 3 miles long and 1.5 miles wide, was a lake of liquid fire. Lava fountains rose and fell like liquid music. The heat was so intense that they could only approach the rim for brief periods before retreating to cool down. The sound was indescribable, a deep, continuous roar punctuated by explosions as pockets of gas burst through the surface of the lava lake. The ground vibrated beneath their feet. The air smelled of sulfur and hot rock. But McDonald knew that this spectacular summit activity might only be the beginning. The real danger would come if the eruption shifted to the rift zones, sending lava flows down toward populated areas. As dawn broke on June 2nd, the character of the eruption began to change. The summit fountains were still active but diminishing. The seismic activity had shifted, migrating down the mountain's flanks. By mid-morning, it was clear what was happening. The magma was moving laterally underground, following the southwestern rift zone. At 10:30 a.m., the southwestern rift zone split open. The breach was dramatic and devastating. 13 separate fissures tore through the landscape between 11,000 and 12,000 feet elevation, each one spewing curtains of fire that rose hundreds of feet into the air. The combined output was staggering. Geologists would later estimate that in the first 3 hours alone, more than 100 million cubic yards of lava poured from these vents. This was not a single eruption. This was a wholesale breaching of the mountain's flank, a catastrophic release of pressure that had been building for years. The lava that emerged was pahoehe in its initial stages, the Hawaiian term for smooth, ropey lava that flows like thick honey. It was incandescent orange, nearly white at its hottest points, with temperatures exceeding 2,000 degrees Fahrenheit. As the lava poured from the fissures, it flowed downslope, following the natural drainages and valleys carved by previous eruptions. The flows were fast in some sections. They advanced at speeds exceeding 20 miles per hour, faster than a person could run. But as the lava traveled downslope, cooling and degassing, much of it transformed into rough, jagged lava that advances more slowly but is equally destructive. Flows bulldoze everything in their path, grinding vegetation to ash, crushing buildings, moving forward in a tumbling, clinking mass of incandescent rubble. Multiple flows began their descent toward the southwestern coast, each one carving its own path through the landscape. The largest flow, later designated the Ho'okina flow by geologists, moved with terrifying purpose toward the small communities scattered along the Kona coast. Within hours, the flows had descended below 8,000 feet elevation. By nightfall, they had reached 5,000 feet. The advance seemed unstoppable, a river of molten rock more than half a mile wide in places, glowing like a wound in the earth's side. Residents of the threatened communities watched the advancing flows with a mixture of fascination and dread. Some evacuated immediately, loading possessions into trucks and cars, driving toward safer ground. Others stayed, unwilling to abandon their homes, hoping the flows would divert or stop before reaching them. Civil defense officials worked frantically to evacuate the most threatened areas. Roads were cleared, emergency shelters were opened. But the logistics were complicated by the remote nature of many of the communities and the limited infrastructure available. And then, on June 3rd, the character of the eruption shifted again. The fissures high on the mountain's southwestern flank began to wane. The lava output decreased. The flows that had been racing downslope began to slow, congealing, hardening, losing their forward momentum. For a brief moment, it seemed the worst might be over. But the seismic activity had not decreased. It had simply shifted, moving northeast toward the opposite side of the mountain, toward Hilo. To understand what happened next, to grasp the forces that would reshape the landscape and threaten thousands of lives, we must journey beneath the mountain into the deep architecture of Earth itself. The Hawaiian Islands exist because of a phenomenon so extraordinary that geologists initially struggled to explain it: a volcanic hotspot. The theory of plate tectonics, which revolutionized geology in the 1960s, explains most volcanic activity as occurring at the boundaries between tectonic plates. Where plates collide, one is forced beneath the other in a process called subduction, and the melting of this descending plate produces the magma that feeds volcanoes like Mount Fuji, Mount St. Helens, and Krakatoa. Where plates pull apart as they do along the mid-Atlantic ridge, magma wells up from below to fill the gap, creating new oceanic crust. But Hawaii is different. The Hawaiian Islands lie in the middle of the Pacific Plate, thousands of miles from the nearest plate boundary. By all logic, there should be no volcanoes here. The solution to this puzzle came from a Canadian geologist named Ye Tuzo Wilson, who in 1963 proposed the existence of mantle plumes, columns of hot rock rising from deep within the Earth's mantle. Deep beneath the Pacific Ocean floor, nearly 2,000 miles below the surface, a plume of superheated rock rises from the boundary between Earth's mantle and core. This boundary, known as the core mantle boundary or D layer, is one of the most extreme environments on Earth. Temperatures exceed 7,000 degrees Fahrenheit. Pressures are millions of times atmospheric pressure. In this infernal landscape, thermal anomalies can develop regions where the rock is slightly hotter than its surroundings. Because hotter rock is less dense, it becomes buoyant, rising slowly through the overlying mantle like a blob of wax in a lava lamp. This rising plume takes millions of years to reach the surface. As it rises, the pressure decreases. Eventually, usually when the plume reaches a depth of about 60 miles below the surface, the pressure becomes low enough that the rock begins to melt. This is how most of Earth's magma is produced, not by adding heat, but by reducing pressure. The rock is hot enough to melt all along, but the enormous pressure keeps it solid. Reduce the pressure and it liquefies. The magma produced by this partial melting is less dense than the solid rock around it, so it continues to rise. It accumulates in chambers and reservoirs, pools beneath the Earth's crust, searches for weaknesses through which it can escape. And eventually it erupts. This mantle plume beneath Hawaii is fixed in place, anchored to the deep Earth. But the tectonic plates above it are not fixed. They move, driven by convection currents in the mantle. The Pacific Plate, a massive section of Earth's crust spanning millions of square miles, drifts northwest at a rate of about 3 inches per year. As it moves over the stationary hotspot, the plume burns through the plate like a blowtorch through steel, creating volcanoes. Over millions of years, this process has created the entire Hawaiian island chain. Each island is a volcano, or in most cases, a cluster of volcanoes that formed over the hotspot and then drifted away as the Pacific Plate carried it northwest. The oldest Hawaiian islands are now mere seamounts, completely eroded below sea level, located far to the northwest. The Emperor Seamounts, which form a line extending almost to the Kamchatka Peninsula, are the oldest evidence of the Hawaiian hotspot, some of them more than 70 million years old. Closer to the current position of the hotspot, the islands become progressively younger. Kauai, the oldest of the major islands, is about 5 million years old. Oahu is 3 million years old. Maui is less than 1 million years old. And the Big Island Hawaii is less than 700,000 years old. It sits directly above the hotspot, receiving a constant supply of fresh magma from the deep plume below. But even the Big Island is moving, carried northwest by the Pacific Plate at the same slow but inexorable pace. In a few 100,000 years, it too will have drifted away from the hotspot. Its volcanoes will go dormant, their connection to the deep magma source severed. And already a new island is forming to take its place. Beneath the waves, 20 miles southeast of the Big Island, a volcano is rising from the ocean floor. Named Lo'ehi, this seamount has already grown to a height of more than 10,000 feet above the seafloor. Its summit is still about 3,000 feet below the ocean's surface, but it is growing. Lo'ehi erupts regularly, adding layer upon layer of lava to its summit. In perhaps 50 to 100,000 years, an eye blink in geological time, it will breach the surface and become Hawaii's newest island. This is the Hawaiian Hotspot Trail, a geological conveyor belt that has been building islands for 70 million years, and will continue to do so for millions of years to come. Mauna Loa sits directly above the hotspot's most intense heat. It is the largest volcano in the Hawaiian chain, the product of at least 700,000 years of nearly continuous volcanic activity. Beneath its summit, several miles underground, lies a vast reservoir of magma, a chamber several miles wide and perhaps a mile or more thick. This chamber is constantly being replenished from below, fed by the rising plume of hot mantle rock. As this chamber fills, pressure builds. The rock surrounding the chamber expands. Fractures develop and propagate through the mountain's interior. The entire edifice inflates, like a balloon being slowly filled with air. This inflation can be measured. Modern GPS stations detect the vertical and horizontal movement of the ground with millimeter precision. The summit of Mauna Loa typically rises several centimeters per year between eruptions as the magma chamber fills. When the pressure exceeds the strength of the surrounding rock, when the volcano can no longer contain the magma within fractures open, providing a pathway to the surface. This is an eruption. But the character of the eruption depends critically on the nature of the magma itself. Mauna Loa's magma is basaltic, low in silica, silicon dioxide, high in iron and magnesium, and crucially low in dissolved gases and low in viscosity. Viscosity is the key. It measures how easily a fluid flows. Water has low viscosity, honey has higher viscosity, and cold molasses has very high viscosity. Magma viscosity depends primarily on two factors: temperature and silica content. Hot magma is less viscous than cool magma. Low silica magma is less viscous than high silica magma. Hawaiian basaltic magma is both hot, around D-2,200 degrees Fahrenheit, and low in silica, about Y, COs by weight. This makes it extraordinarily fluid. It flows almost like water in its initial stages. This fluidity has profound implications for eruptive behavior. In contrast, consider a volcano like Mount St. Helens or Vesuvius. These volcanoes erupt andesitic or rhyolitic magma high in silica, 60 to 75% COs, cooler, PA-1800 degrees Fahrenheit, and therefore much more viscous. Viscous magma traps gases. As the magma rises and pressure decreases, these dissolved gases want to escape like bubbles forming in a soda when you open the bottle. But the thick, sticky magma doesn't let them escape easily. The result is explosive eruption. The magma literally tears itself apart, blasting rock, ash, and gas miles into the sky. Hawaiian basaltic magma, by contrast, is so fluid that gases escape relatively easily. The eruptions are effusive rather than explosive. The magma flows out rather than blowing up. This is why Mauna Loa is a shield volcano, a broad, gently sloping mountain built by countless layers of runny lava flows. Its profile resembles a warrior's shield laid upon the ground, with slopes that rarely exceed 10 degrees. The contrast with stratovolcanoes is dramatic. Mount Fuji, Mount Rainier, Mount Shasta, these classic cone-shaped mountains, have steep slopes of 30 degrees or more, built by alternating layers of viscous lava and ash from explosive eruptions. But don't mistake gentleness of slope for gentleness of behavior. Hawaiian lava flows can travel at speeds exceeding 30 miles per hour down steep slopes. They can cover vast distances in mere hours. They maintain temperatures above 2,000 degrees Fahrenheit for days or weeks. And in 1950, they were heading toward Hilo. At 2:30 a.m. on June 3rd, the northeastern rift zone erupted. The breach occurred without warning. One moment, the mountain was quiet except for the persistent seismic tremor. The next moment, the ground split open in a series of parallel fissures between 10,000 and 11,500 feet elevation. A curtain of fire erupted from these fissures, shooting lava hundreds of feet into the air. The fountains were even more vigorous than those from the southwestern eruption, driven by fresh magma rising directly from the depths. The sound was like nothing the island had experienced in modern times, a deep continuous roar that could be heard 50 miles away, punctuated by sharp cracks of underground explosions, as magma forced its way through solid rock by the hiss of superheated gases escaping at supersonic speeds. From Hilo, the eruption was clearly visible even in the pre-dawn darkness. An orange glow illuminated the mountain's flank. Fountains of lava danced against the night sky. Residents who had been sleeping were awakened by the sound, by neighbors shouting, by car horns honking as people drove through the streets spreading the alarm. Dr. McDonald and his team at the observatory scrambled to respond. They had been expecting this. The seismic data had clearly shown the magma migrating northeast, but the intensity of the eruption exceeded their worst predictions. Multiple survey teams were dispatched to track the flows. In 1950, In 1950, this meant driving as close as possible to the eruption site and then observing from whatever vantage points could be safely reached. There were no satellites, no drones, no thermal cameras. Just human observers with binoculars, notebooks, and cameras, trying to document one of nature's most powerful phenomena. What they observed was both magnificent and terrifying. The lava fountains from the northeastern rift zone vents were producing an enormous volume of lava. Later estimates would suggest a discharge rate of more than 300 cubic yards per second in the first hours of the eruption. This is roughly equivalent to filling an Olympic-sized swimming pool every 8 seconds. All of this lava was flowing downslope, northeast toward Hilo. The initial flows were pahuiho, moving fast across the higher elevations. They flowed in channels and tubes, insulated by their own solidified crust, maintaining their heat and fluidity across miles of terrain. As the flows descended below 8,000 feet, they began to encounter vegetation, first the sparse alpine plants, then increasingly dense forest. Trees exploded as the lava advanced. The moisture inside their trunks turned to steam in seconds, building pressure until the wood literally detonated, scattering burning splinters across the landscape. Fires erupted ahead of the main flow, ignited by radiant heat alone. The temperature near the flow front was hot enough to ignite wood from dozens of yards away. By dawn on June 3rd, the flows had traveled more than 5 miles from the vent. By noon they had covered 10 miles. The advance was relentless, faster than any Hawaiian flow in recorded history. The flow followed natural drainages, cutting through the forest like a burning river. Where it encountered flatter terrain, it spread laterally, creating lobes and fingers that searched for the path of least resistance. The people of Hilo watched the mountain with a mixture of awe and dread. By day, they could see the enormous steam plume rising from the vents, white against the blue sky, visible from anywhere on the eastern side of the island. By night, the glow painted the mountain's flank a hellish red, pulsing with the rhythm of the fountains. Journalists and photographers from around the world descended on the island. This was front-page news. One of Earth's largest volcanoes was erupting, threatening a city of tens of thousands. Newsreels captured images of the lava rivers, the fountaining vents, the families loading possessions into trucks just in case. One reporter described the scene as a biblical vision of the end times, fire and brimstone made manifest. But for the residents of Hilo, this was not abstract drama. This was their lives, their homes, their community hanging in the balance. Civil defense authorities faced the agonizing decision of whether to order evacuation. The flow was still more than 15 miles from the city, traveling through largely agricultural land and forest. An evacuation would be massively disruptive. Where would thousands of people go? How long would they need to stay away? What about the economic impact? But if the flow continued at its current pace and direction, it would reach Hilo's outskirts within a week, perhaps less. The decision was complicated by the nature of lava flows. Unlike hurricanes, which follow predictable paths, or floods, which can be modeled with reasonable accuracy, lava flows are capricious. They follow topography, but they also create their own channels, build their own levees, and can shift direction with little warning. A flow can travel 20 miles in 2 days, then stall for no apparent reason when the supply of new lava from the vent decreases. Or it can suddenly accelerate when a new surge of magma breaks through, bringing fresh momentum to a slowing flow. Scientists could provide probability estimates, but not certainties. The flow might reach Hilo. It might stop 10 miles short. It might divert to the north or south, missing the city entirely. How do you make life and death decisions based on probabilities? Governor Ingram Steinbeck toured the threatened areas by helicopter, seeing firsthand the awesome power of the advancing flow. He conferred with civil defense officials, with Dr. McDonald, with community leaders. The decision was made to prepare for evacuation, but not to order it immediately. Evacuation routes were identified and marked. Emergency shelters were designated and stocked. Hospitals made plans to relocate patients. But for now, people could stay in their homes, watching and waiting. One photograph from that time shows a sugar plantation owner standing on a hill, watching the advance of the flow toward his fields. He holds a hat in one hand, shading his eyes from the sun. His expression is unreadable resignation, perhaps, or the stoic acceptance that comes from living in a place where paradise and peril are inseparable. Behind him, you can see the orderly rows of sugar cane, green and ready for harvest. Beyond that, a line of trees. and beyond that, a wall of black rock, 40 feet high in places, advancing at a walking pace. By June 5th, the flow had traveled 15 miles from the vent. It had consumed the tiny settlement of Ho'oku'u, reducing homes and churches to rubble buried beneath 40 feet of rock. The few families who lived there had evacuated days earlier, watching from distant hillsides as their homes disappeared. The lava was now entering the Waiakea Forest Reserve, a dense jungle that provided a natural barrier between the flow and the more populated areas beyond. Civil defense hoped that the forest would slow the continued 512 pamvents, that the flow would spread and thin as it encountered the flatter terrain. For a time, this seemed to be happening. The flow's forward edge, which had been moving at speeds up to half a mile per hour, slowed to a few hundred feet per hour as it spread across the forest floor. But it did not stop. The advance through the forest was apocalyptic. The lava consumed everything trees centuries old, native birds' nests, rare plants found nowhere else on Earth. The johi'a trees, which dominate Hawaiian forests, exploded one after another as the flow advanced. Their wood, saturated with moisture from the frequent rains, could not withstand the sudden transition from cool jungle to 2,000-degree inferno. The sound of trees exploding was like distant gunfire, a continuous popping that could be heard miles away. Between the explosions, the roar of the flow itself, the rumble and crack of solidified crust breaking apart, the hiss of steam where lava encountered moisture, the deep bass note of gases escaping from the interior of the flow. And beneath it all, a subsonic vibration that you felt more than heard, a tremor in the bones that reminded you that the earth itself was in motion. By June 7th, the flow had reached the Hilo Highway, the main artery connecting the east and west coasts of the island. This two-lane road, built in the 1930s, was a lifeline for commerce and transportation. Its loss would effectively cut the island in half. Highway crews worked frantically to reroute traffic before the flow arrived. Heavy equipment was moved to safety. Warning signs were erected miles in advance. Some optimists suggested building barriers to protect the road or to divert the flow. Bulldozers scraped up berms of earth and rock across the lava's projected path. But these efforts were futile. The flow simply pushed through the barriers or flowed around them or buried them completely. You cannot negotiate with lava. You cannot reason with it or bribe it or threaten it. It flows according to the laws of physics, gravity, viscosity, volume, and those laws do not bend for human convenience. When the flow reached the highway on the evening of June 7th, it crossed in less than an hour. The asphalt burst into flame as the lava approached. Then it liquefied, mixing with the molten rock, vanishing beneath the advance. By midnight, the road was buried under 20 feet of lava. The flow continued northeast. By June 10th, it advanced to within 8 miles of Hilo's airport. The airport, built just before World War II, was critical infrastructure not just for civilian travel, but for military operations. The United States Air Force maintained a presence there, and in the early days of the Cold War, strategic considerations weighed heavily on any decision-making. Dr. McDonald and his team were providing daily updates to civil defense and military authorities. They had established observation posts along the flow's margins, taking measurements every few hours. Surveyors used precise instruments to measure the flow's advance rate, its width, its thickness. The data showed that the flow was gradually slowing. The advance rate, which had been more than half a mile per hour at higher elevations, had decreased to about a quarter mile per hour by June 10th. The flow was spreading laterally, thinning, losing heat to the surrounding environment, but it was still advancing. Governor Steinbeck ordered the evacuation of the Waiakea area, the neighborhood closest to the advancing flow. Families packed what they could carry and left their homes, many of them for the last time. Emergency shelters filled with displaced residents, some angry, some resigned, most simply exhausted by the uncertainty. Hilo's business district prepared for the worst. Store owners moved inventory to higher ground. Banks transferred records and cash to branches on other islands. The port prepared to relocate operations. If the flow reached the city, the damage would be catastrophic, not just from the direct destruction of buildings, but from the economic impact. Hilo was the Big Island's commercial hub. Its port handled most of the island's imports and exports. Losing it would devastate the island's economy for years, perhaps decades. The entire population of the Big Island was about 70,000 in 1950. Hilo accounted for more than a third of that. Where would they all go if the city had to be evacuated? How long would they be displaced? How could the island function without its largest town? These were the questions that kept Governor Steinbach awake at night, that weighed on Dr. MacDonald's mind as he made his calculations and wrote his reports. By June 12th, the flow had advanced to within 4 miles of Hilo's airport. Evacuation plans were finalized. Civil defense identified routes and schedules. Hospitals prepared to relocate patients to facilities in other towns. Military aircraft were placed on standby to evacuate critical personnel and equipment. The flow was now moving through the Kaumana area, destroying homes and farms that had been there for generations. Families who had refused to evacuate earlier finally relented, loading trucks with whatever possessions they could save and joining the exodus. But even as the crisis reached its peak, Dr. MacDonald noticed something in the data. The flow's advance rate had decreased again. By June 12th, it was moving only a few hundred feet per hour. The discharge rate from the vents appeared to be declining. The fountains were lower, the volume less. The eruption might be waning, but might is not a word you can base an evacuation on. Governor Steinbach ordered civil defense to proceed with preparations for a full evacuation of Hilo, waterfront, and low-lying areas. June 13 dawned hot and humid, with clouds building over the mountain as they did most afternoons. The flow was now within 4 miles of the airport, close enough that observers could see individual trees igniting on its leading edge. And then, as the afternoon wore on, something changed. The flow stopped advancing. The cessation was not dramatic. There was no final surge, no sudden cooling, no visible change in the flow's appearance. The leading edge simply stopped moving forward. Scientists monitoring the vents reported that the lava fountains had decreased significantly. The supply of new lava, the fresh magma that had been driving the flow's advance, had diminished to a trickle. By evening on June 13th, the flow was visibly stalling. The orange glow at the leading edge faded to dull red, then to black as the exposed surface cooled and solidified. The northeastern rift zone fissures, which had poured out lava continuously for 10 days, began to quiet. The fountains diminished. The deep roar that had been audible across the island faded to a hiss, then to silence. The eruption was over. Hilo had been spared again. The relief was palpable. Church bells rang across the city. Families who had evacuated began to return, finding their homes intact but covered in a layer of volcanic ash. Store owners reopened their businesses. The port resumed normal operations. But the landscape had been transformed. The northeastern flows covered more than 100 square miles, bearing forests, farms, villages, and roads beneath rock that in places was more than 50 feet thick. The flow that had threatened Hilo stopped just 3.5 miles from the city limits, close enough to smell, close enough to feel the radiant heat on still nights, but not close enough to destroy. The southwestern flows, though they had received less attention due to the threat to Hilo, had been equally destructive. They had reached the ocean at several points, extending the island's coastline by hundreds of yards. Where the lava met the sea, enormous clouds of steam erupted, creating localized rainstorms of corrosive hydrochloric acid as the volcanic glass interacted with seawater. In total, the 1950 eruption of Mauna Loa produced approximately 420 million cubic yards of lava-enough material to bury the entire island of Manhattan under more than 20 feet of rock. The flows destroyed dozens of homes, thousands of acres of agricultural land, and miles of roads and infrastructure. The tiny village of Ho'oku'u was completely obliterated, its location now marked only by archival photographs and the memories of those who had lived there. But remarkably, no lives were lost. This was a testament to several factors: the relatively slow, predictable nature of Hawaiian lava flows, which gave people time to evacuate, the effective monitoring and warning system maintained by the Hawaiian Volcano Observatory, and the cooperation of residents who heeded evacuation orders despite the disruption and uncertainty. The economic cost was significant but manageable. Insurance companies paid out claims for destroyed property. The territorial government provided assistance for displaced families. Within a year, most of the affected areas had recovered, though the land itself would bear the scars for centuries. But the psychological impact lingered. The people of Hilo had watched an inexorable river of fire approach their city for 10 days, knowing that they were powerless to stop it, that their fate rested on geological processes they could barely understand. The question that haunted every conversation, every late-night discussion: Every planning meeting for years afterward was simple and terrible. What about next time? The 1950 eruption was not an anomaly. It was not even particularly unusual by Mauna Loa's standards. It was simply a reminder, a demonstration of the volcano's power and the precariousness of life in its shadow. Mauna Loa erupts on average every 6 years. This average conceals considerable variability. Sometimes eruptions occur only a year or two apart, while other times, decades pass between events. But the overall pattern is clear. Mauna Loa is one of the most active volcanoes on Earth. Since 1843, when reliable record-keeping began, the volcano has produced 33 confirmed eruptions. Before that, Hawaiian oral traditions and geological evidence suggest eruptions occurred with similar frequency going back centuries, perhaps millennia. Each eruption has its own character, its own story. Some are brief, lasting only hours or days, producing relatively small volumes of lava. Others continue for months, reshaping vast sections of the landscape. The 1855 to 1856 eruption lasted 13 months, one of the longest in recorded history. Lava flowed almost continuously, threatening Hilo on multiple occasions but never quite reaching it. The 1868 eruption was accompanied by one of the largest earthquakes ever recorded in Hawaii, estimated at magnitude 7.9. The earthquake triggered massive landslides that killed dozens of people, making it one of the deadliest natural disasters in Hawaiian history. The eruption itself was almost an afterthought, producing relatively modest lava flows overshadowed by the earthquake's devastation. The 1881 eruption, as we've seen, brought lava to the shores of Hilo Bay, where Princess Ruth's prayers or simple good fortune stopped the advance just in time. The 1899 eruption lasted 6 weeks, producing flows that reached the ocean but threatened no major settlements. The 1907 eruption lasted just 15 days, but produced some of the fastest lava flows ever measured in Hawaii, racing down the mountain's flank at speeds exceeding 30 miles per hour. The 1914 to 1915 eruption continued for almost 6 months, one of the most voluminous eruptions in Mauna Loa's modern history. The 1926 eruption threatened the village of Ho'oploa on the west coast, destroying several buildings before the lava stopped just short of the main settlement. The 1935 eruption marked a turning point in volcano management. When lava flows threatened Hilo yet again, the U.S. Army Air Corps conducted an experimental aerial bombing campaign, dropping 2,600-pound bombs on the lava channels in an attempt to divert the flow. The bombing was dramatic but of questionable effectiveness. Some claimed it helped divert the lava away from Hilo. Others pointed out that the eruption was already waning and the flow would have stopped anyway. The debate continues to this day, but the bombing remains one of the most controversial volcano intervention attempts in history. The 1942 eruption occurred during World War II, when Hawaii was under martial law following the Pearl Harbor attack. The eruption was carefully monitored but kept relatively quiet in the press to avoid providing intelligence to Japanese forces. The 1949 eruption lasted just 3 weeks, producing flows on the southwestern rift zone that reached the ocean. And then came 1950, the eruption we have examined in detail. After 1950, Mauna Loa's eruptive frequency began to decrease, a fact that initially puzzled volcanologists. The volcano remained active, but the intervals between eruptions grew longer. And then ... silence. The 1975 eruption was brief but significant. It lasted less than a day, only about 22 hours, but produced lava flows that moved with extraordinary speed. The flows traveled more than 6 miles in the first 3 hours, achieving rates of advance that remain among the fastest ever documented for Hawaiian lava. These flows raced down the southwestern rift zone, following valleys and drainages with liquid efficiency. They reached the ocean in less than 3 hours, faster than anyone thought possible. The speed was attributable to several factors. The flows remained fluid and hot because they moved so quickly they had little time to cool. The steep slopes in the upper elevations provided rapid acceleration, and the volume of lava being discharged was enormous, creating deep channels that insulated the interior of the flow. Fortunately, the flows traveled through largely unpopulated areas. No major communities were threatened. But the eruption served as a reminder that Mauna Loa's behavior could not be taken for granted. Each eruption was unique, capable of surprising even experienced volcanologists. The 1984 eruption was, in many ways, a replay of 1950, but with better monitoring. better warning systems, and better public communication. It began on March 25, 1984, with summit activity that quickly migrated to the northeastern rift zone. Within hours, lava was pouring from fissures between 9,000 and 12,000 feet elevation, heading directly toward Hilo. But this time, the Hawaiian Volcano Observatory was equipped with modern technology. Seismograph networks detected the magma's movement with precision. Electronic tilt meters measured ground deformation in real time. Gas sensors analyzed volcanic emissions. And most importantly, communication systems allowed instant sharing of data with civil defense and emergency management. Dr. Robert Decker, the observatory's director in 1984, coordinated a massive monitoring effort. Observation posts were established at strategic locations. Helicopter overflights provided regular updates on the flow's progress. Computer models attempted to predict the flow's path and advance rate. For 3 weeks, the world watched as lava crept toward Hilo. Television cameras broadcast live images of the advancing flow. News helicopters provided aerial footage. The eruption became a global media event. Civil defense prepared for the worst. Evacuation routes were tested. Shelters were stocked. The National Guard was mobilized. Plans were made to relocate the airport if necessary. And once again, at the last possible moment, the flow stopped. It halted just 4.5 miles from the city limits, closer than in 1950. Close enough that the glow from the flow front could be seen from downtown Hilo, but not close enough to cause destruction. The relief was mixed with a growing sense of unease. How many times could Hilo be lucky? How many times could the flow stop just short? Geological time is patient. Eventually, the odds would run out. And then, after 1984, Mauna Loa went quiet. Years passed, then a decade, then 2 decades, then 3. By the early 2000s, an entire generation of Big Island residents had grown up without experiencing a Mauna Loa eruption. The volcano had become part of the scenery, a beautiful backdrop to daily life, admired but not feared. But the scientists at the Hawaiian Volcano Observatory never forgot. They maintained their monitoring networks. They analyzed every earthquake, every millimeter of ground deformation, every gas emission. And they knew that the silence could not last forever. Mauna Loa was still active. Magma was still accumulating beneath the summit. The pressure was still building. The longer the interval between eruptions, the larger the eventual eruption would likely be. Like a pressure cooker with the valve closed, the volcano was storing energy. By 2020, seismic activity beneath Mauna Loa had begun to increase. Earthquakes became more frequent, more shallow. The summit was inflating again, rising several centimeters per year. The signs were clear. The mountain was awakening. On November 27, 2022, after 38 years of silence, Mauna Loa erupted again. The awakening came with less warning than in 1950 or 1984. Seismic activity had been elevated for months, but the actual onset of the eruption was rapid. At 11:30 p.m., the summit caldera Mokuioio breached. Within minutes, lava fountains shot into the night sky. By midnight, fissures had opened on the northeastern rift zone between 11,000 and 12,000 feet elevation. Once again, the lava was heading toward Hilo. But this was 2022. Not 1950. The world was connected in ways that would have seemed like science fiction to Dr. McDonald and his contemporaries. Webcams captured the fountains of lava against the night sky, streaming live video to millions of viewers worldwide. Drones flew over the flows, providing high-definition footage from angles that would have been impossible in previous eruptions. Satellites measured the thermal output of the eruption every few minutes, tracking the flows with infrared sensors that could see through clouds and darkness. Social media exploded with images, videos, and commentary. People from around the world watched in real time as one of Earth's largest volcanoes unleashed its power. The Hawaiian Volcano Observatory, now part of the U.S. Geological Survey, deployed an unprecedented array of monitoring technology. GPS stations measured ground deformation to the millimeter. Dense seismometer networks detected earthquakes too small for humans to feel, tracking the movement of magma underground. Gas sensors analyzed the chemical composition of volcanic emissions, looking for clues about the magma's depth, temperature, and evolution. Laser scanning systems created 3-dimensional maps of the flows, updated every few hours, showing exactly where the lava had traveled and where it might go next. Computer models, running on supercomputers, simulated the flow's behavior based on real-time data, generating probabilistic forecasts of which areas were most at risk. All of this information was shared immediately with civil defense authorities, emergency managers, and the public. Maps were updated online. Press conferences provided regular updates. Evacuation routes were identified and publicized. The 2022 eruption lasted 2 weeks, producing lava flows that traveled nearly 15 miles from the vent. The flows followed a similar path to those in 1950 and 1984, moving northeast through the Waiakea forest toward the populated areas beyond, but this time, the advance was slower. The discharge rate was lower than in previous eruptions. The flows spread laterally, thinning and cooling, losing momentum as they traveled. By December 10th, the flows had stalled. The vents had gone quiet. The eruption was over. No homes were destroyed. No evacuations were ordered. The lava stopped well short of any major infrastructure. But the message was clear: Mauna Loa is not dormant. It is not even resting, it is merely pausing between breaths. And the next breath could come at any time. The Hawaiian Islands are, in a very real sense, a laboratory for understanding volcanic processes. Nowhere else on Earth can scientists study shield volcanoes with such access, such instrumentation, such a detailed historical record. The Hawaiian Volcano Observatory has become one of the world's premier volcano research facilities. Scientists from dozens of countries come to Hawaii to study eruptions, to test new monitoring techniques, to refine theoretical models. Every eruption of Mauna Loa and Kilauea adds to our knowledge. Every flow teaches us something new about how magma moves, how lava behaves, how volcanic landscapes evolve. We have learned that Hawaiian eruptions, while generally less explosive than those of stratovolcanoes, follow complex patterns that can be difficult to predict. The location where magma will emerge, the volume that will be erupted, the speed and direction of the resulting flows, all of these depend on factors that are only partially understood. We have learned that precursory seismic activity, while generally reliable as a short-term warning sign, can sometimes be ambiguous or misleading. The 2022 eruption, for example, began with less seismic warning than expected. We have learned that lava flows, even in Hawaii, can move with surprising speed under certain conditions. The 1975 flows remain a reminder that gentle Hawaiian eruptions can still be dangerous. We have learned that long repose periods do not necessarily mean larger eruptions. The 2022 eruption, after 38 years of silence, was actually smaller than the 1984 eruption, which came just 9 years after the previous one. And we have learned that despite all our technology, all our monitoring networks, all our computer models, we still cannot control volcanic eruptions. We can only watch, measure, and try to keep people out of harm's way. Living with an active volcano requires a particular kind of courage or perhaps a particular kind of acceptance. The residents of Hilo, Kona, and the dozens of smaller communities scattered across the Big Island know the risks. They know the statistics. They know that sooner or later another flow will threaten their homes, their livelihoods, their carefully constructed lives. And yet they stay. Some stay because Hawaii is home, because their families have lived here for generations, because leaving would mean abandoning not just a place, but an identity. The connection to the land, to this specific land, with its volcanic soil and tropical beauty, runs deeper than rational risk calculation. Others stay because the volcanic soil is incredibly fertile, producing coffee, macadamia nuts, tropical fruits, and flowers that cannot be grown as well anywhere else. The same volcanic processes that destroy also create new land, rich soil, unique ecosystems. Still others stay because the beauty of the islands outweighs the danger. Where else can you swim in the ocean in the morning and ski on Mauna Kea in the afternoon? Where else can you see lava flowing into the sea, creating new land before your eyes? Where else is the raw power of geological processes so visible, so accessible, so awe-inspiring? And some stay because they understand on a fundamental level that risk is the price of living anywhere. Earthquakes threaten California. Hurricanes ravage the Gulf Coast. Tornadoes tear through the Great Plains. Floods inundate river valleys. Wildfires consume forests. Nowhere is truly safe. Hawaii is simply more honest about its dangers. The volcanic hazard maps produced by the U.S. Geological Survey divide the Big Island into 9 hazard zones, ranging from Zone 1, highest hazard, to Zone 9, lowest hazard. Large portions of the island, including much of Hilo, fall into zones 1 through 3 areas likely to be affected by lava flows within a human lifetime. Real estate transactions include mandatory disclosures about volcanic hazards. Lava zone information appears on property listings. Insurance companies factor volcanic risk into their premiums if they offer coverage at all. Some areas are essentially uninsurable, at least for volcanic damage. Yet development continues. New homes are built on land that has been covered by lava within living memory. Subdivisions expand into high-risk zones. The population grows. This is not ignorance or denial. Most residents understand the risks perfectly well. It is a calculated choice, a decision that the rewards of living in paradise outweigh the possibility of disaster. The native Hawaiian understanding of Pele, the volcano goddess, contains a profound truth about the relationship between humans and geological forces. Pele is not evil in Hawaiian mythology. She is not a malevolent deity seeking to harm humans. She is creative and destructive in equal measure, building islands even as she buries villages, creating land even as she claims it back. She is described as passionate, temperamental, jealous, powerful, very human characteristics projected onto geological processes. Stories tell of Pele traveling in disguise as an old woman, testing the hospitality of humans. Those who show her kindness are spared when the lava flows. Those who are rude or inhospitable find their homes buried. These stories encode practical wisdom. Be kind to strangers, because you never know who they might be. Respect the land because it can be taken away. Build with the understanding that nothing is permanent. Modern science has replaced the goddess with tectonic plates and magma chambers, with chemical processes and physical laws. We understand the mechanisms by which magma rises, why some eruptions are explosive and others effusive, how lava flows behave under different conditions. But the fundamental truth remains: volcanoes create the very ground we stand on. They generate atmospheric gases, including the oxygen we breathe, oxygen, that was originally released from volcanic activity early in Earth's history. They cycle nutrients from the deep earth to the surface, enriching soils. They create the geological diversity that drives biological diversity. The Hawaiian Islands would not exist without Mauna Loa and its siblings. The incredible biodiversity, the unique species found nowhere else on Earth, evolved in an environment created by volcanism. The Hawaiian honeycreeper birds, with their bewildering array of beak shapes, adapted to different food sources. The silversword plants, growing only on volcanic cinder cones at high elevation. The Hawaiian monk seal, the most endangered seal species in the world, breeding on beaches that are themselves products of volcanic activity. Paradise and peril are not opposites. They are partners, two sides of the same geological coin. You cannot have the islands without the volcanism. You cannot have the fertile soil without the lava flows. You cannot have the dramatic landscapes without the geological violence that created them. This is the bargain. This is the price of paradise. Today, more than 200,000 people live on the Big Island of Hawaii. The population has nearly tripled since 1950. Thousands more visit everyday tourists seeking sun and surf, adventure and beauty, a taste of tropical paradise. The economy is robust and diverse, built on tourism, agriculture, astronomy, renewable energy, and increasingly remote work, as high-speed internet makes the island accessible to those who can work from anywhere. Development continues to expand, creeping closer to the rift zones, encroaching on areas that have been covered by lava within living memory. Real estate prices have soared, driven by demand from both locals and mainlanders seeking vacation homes or retirement properties. New subdivisions rise on old lava flows. The black rock is bulldozed and graded, roads are paved. Homes are constructed. Landscaping transforms the barren lava into lush gardens. Hotels are built with views of the volcanoes, advertising their proximity to one of the world's most active volcanic regions as a selling point, not a liability. And every real estate transaction includes the disclosure: this property may be subject to volcanic hazards, maybe. Not will be. Not is certainly subject to, maybe. It is a hedge, a linguistic buffer between knowledge and acceptance, between scientific understanding and emotional reality, but geology does not deal in maybes. Mauna Loa will erupt again. Not may erupt, or might erupt, or could possibly erupt under certain conditions. Will erupt. The only questions are when, where, and how severely. The Hawaiian Volcano Observatory maintains its vigil from its new location on the University of Hawaii at Hilo campus. Having moved from its original location on Kilauea's rim after that building was damaged by earthquakes and summit collapse in 2018, 24 hours a day, 7 days a week, 365 days a year, scientists and technicians monitor the mountains. Seismometers record every tremor, from magnitude 0.5 earthquakes too small to feel to magnitude 6 events that shake the entire island. GPS stations track every millimeter of ground movement, detecting the inflation and deflation of volcanic edifices. Satellite radar measures the shape of the volcanoes from space, creating maps so precise they can detect changes of a few centimeters. Gas monitoring stations sample the air continuously, measuring sulfur dioxide, carbon dioxide, hydrogen sulfide, and other volcanic gases. Changes in gas emission rates and compositions can provide clues about magma movement deep underground. Thermal cameras scan the volcano's surfaces, looking for hotspots that might indicate new vents opening or existing vents becoming more active. All of this data flows into computer systems that analyze it in real time, looking for patterns that might indicate an impending eruption. When the next eruption begins, and it will begin, warnings will be issued through multiple channels. Civil defense agencies will be notified immediately. Emergency services will mobilize. Evacuation routes will be activated. The news media will broadcast alerts. Social media will explode with updates. Websites will display maps showing the location of the activity and the areas at risk. People will have time to flee, to save themselves, if not their possessions. But the mountain will not be stopped. No technology we possess can prevent a volcanic eruption. We cannot seal the vents. We cannot cool the magma. We cannot reduce the pressure beneath the mountain. Bombing the lava channels, as the military did in 1935, is ineffective at best and potentially counterproductive. The lava simply flows around the obstacles created by the bombs. Building barriers, walls of earth or rock or concrete, is equally futile. Lava is patient and relentless. It flows around barriers, over them, through them. Given enough time and volume, lava conquers all human obstacles. The best we can do is watch, measure, warn, and evacuate. This is not defeat. This is wisdom, the wisdom to recognize the limits of human power, to accept that some forces are beyond our control. The future of the Big Island is inextricably linked to its volcanic nature. In the coming decades, Kilauea will almost certainly erupt again, as it has been doing almost continuously for the past century. Its behavior is relatively predictable, and its eruptions, while spectacular, rarely threaten large populations directly. Mauna Loa's future is less certain. Its longer repose periods make prediction more difficult. The 2022 eruption ended the 38-year silence, but it's unclear whether the volcano will return to its pre-1950 pattern of frequent eruptions or continue, with long gaps between events. And then there's Loahi, the submarine volcano still building beneath the waves. In perhaps 50,000 to 100,000 years, it will breach the surface. Eventually, it will grow into a new island, continuing the Hawaiian chain into the future. The human response to these future eruptions will depend on many factors: population density, infrastructure development, warning systems, evacuation capabilities, and the lessons learned from past events. Climate change may complicate matters. Rising sea levels will encroach on coastal communities, potentially forcing development into areas at higher risk from lava flows. More intense storms could make evacuation more difficult during eruption emergencies. But the volcanic processes themselves will continue unchanged. The hotspot will keep burning through the Pacific Plate. Magma will keep rising from the depths. Eruptions will keep reshaping the landscape. This is the geological reality of the Hawaiian Islands. This is their nature, their destiny, their gift, and their curse. On clear nights, when the trade winds die down and the stars emerge in their millions, you can stand on Mauna Loa's slopes and feel the mountain breathe beneath your feet. It is subtle, more imagined than felt perhaps, but no less real for that. A slight vibration, a sense of aliveness in the rock, a reminder that beneath the solid-seeming surface lies liquid fire. The mountain is patient. The mountain is massive. And the mountain is alive. 33,000 feet from seafloor to summit, measured from its true base on the ocean floor. 19,000 cubic miles in volume. One of the most massive single mountains on Earth. a structure so large that its weight has depressed the oceanic crust beneath it by 5 miles, creating a moat in the seafloor around its base. It has been here for at least 700,000 years, possibly longer. It was erupting long before the first Polynesians arrived in their voyaging canoes. It was erupting before the first hominids walked upright in Africa. It will be erupting long after our species has passed from the earth. We are visitors in Mauna Loa's domain. Guests in a house we did not build and cannot control. The best we can do is listen, learn, and respect the power that sleeps never soundly beneath the long mountain. Because one day, perhaps tomorrow, perhaps in a decade, perhaps in a century, the ground will shake, the rock will split, and fire will pour forth once more, reshaping the landscape, destroying what we have built, creating something new from the Earth's molten heart. This is not a threat. This is a promise. This is geology. This is Mauna Loa.